Let's start to talk very briefly about the moment. I said, okay, why if I have two boxes and say if I have a box like this here and put the fourth down here it's on the slide, but if I put the fourth on the top, it might roll over. And it was the fact that it's not only the force, the force can generate something that is called moment. And the moment of the force is anytime you have a rotation, you have a moment. For example, when you open the door, they want to open the door. When you push the door does revolve. So because it's revolving around the hinge, what the hinge is, the reason behind it is that your force converted to the moment about the hinge and it causes the door to rotate. If you cannot rotate that, it's not going to happen. So what goes is that if I have a door, so there's a door here, and the hinge, that's the wall. The door there. Here. There's a door there. Usually the knob is here. Right? Yeah. Why you don't put the knob there on the other end? Here.
The moment would be less.
Why don't you, when you say that, why the moment would be less? Because I can, there's a doorknob, I can hold, open the door with a handle. If I put it on the other side, what would happen? You hard to push.
You don't have the same amount of leverage. I can't think of the actual word.
Mechanical advantage.
So if it's harder to push, where I put it, you cannot open the door at all. The doorknob. No matter how much you push it.
On the hinge.
If I put it right here, no matter how much you push it, the door will not open. Ready?
Depends on the door, but yeah.
If I bring it on the other side, I push it, just push it. No matter how much you push it, nothing will happen. And remember that, so I will talk about that. So there's something that's called the moment, and as I said, the moment is something that they cause anything to rotate or revolve, and you call it F equals to, M is equal to Ft.
Yeah, pretty sure that D is the mechanical leverage that we were talking about.
Yeah, you can say that. So if I look at that, if I have a force, if I have a point here, I have a force here, and then D would be this distance here. That's going to be the D, and it's going to be the point O. And then I will say, okay, that moment, what point O would be F times D. So, if you are using the SI, that's going to be in, so it's going to be Newton, it's going to be in meter, it's going to be Newton meter. Just the US unit is going to be pound foot. So it's going to, the force will be pound
we actually using pound foot or are we using Newton meter?
In most problem we use it in metric, but there are some problems that you have it in pound and foot.
Okay.
There's gonna be its units. In case of the 2D momentum. So if I have, for example, the seesaw that talking about it, I have that. So, and then go say, okay, that's it. If I put the F here, then the D would be this distance here. And the moment it causes it to rotate like that. So it goes like that, and you can say, okay, if this is the point O, that moment is about point O, is what the one that causes it to go down. Now, in 2D dimension, I'm going to talk about the 3D and 2D. Here, you can, usually in 2D, you can say, okay, which direction is going to rotate. But, is this positive or negative?
You would normally say negative because it's going downwards.
It is negative, because clockwise is negative.
So, in moment, there is no positive or negative agreed convention. So you are choosing, whenever you are doing, you are choosing, you say, okay, for example, as you said, you can say, okay, counterclockwise is positive, or you can say clockwise is positive. As long as you keep all the sign the same, it's gonna be there. This book, again, we might use another book, it's different. This book considers the counterclockwise positive all the way through. But you can do the same problem, just you assume the clockwise positive. As long as you keep the sign, follow the sign correctly, no, it just be the same. So throughout this book, so it's counterclockwise positive, so this is gonna be, by the convention of this book, would be negative. So we consider counterclockwise book rotation be positive. Now if I have the, so this is the 2D case. If I have the 3D case, that assume that door, probably, so assume these are the hinges, correct? So that's gonna be revolved about that hinges. And here where I'm gonna, is the handle, so where I'm gonna put the force. Right? Now, let's look at it in this way. So, I have the axis, and I have the force about that axis. That's what is called it rotation about that axis. So we'll rotate about that axis. So that's going to be my distance. That's going to be the d. That's going to be perpendicular also here. So the direction of the rotation, I know that it's rotated about that axis. Okay? But when you want, the moment is a vector. When you want to show it, you want to see it, okay, is it, which way to show it? And to show the direction of the moment or the vector of the moment, use the right hand tool, the right hand rule. Remember what I said? If you put your forefinger in the direction of rotation, your thumb gives you the direction of the moment. So here, if it is rotating like that, so the moment would be going up. But it's rotating like that, so the moment would go up. So you have the moment going up. Similar to that, if I have the other gears, so if I have it for example, the F going the other way, this way, then I have that. So it's rotating this direction, so the thumb would be down, so the vector of the M would be down. So that's how we use the right to right hand rule to find out which direction it's gonna rotate. The 2D relatively easy. Question? Well, let's look at some example. So the first example was like that. So if I have the point O and the F, this is going to be D. That the simplest format that we can have. And the moment would go counterclockwise. Right? Now if I move the O a little bit up, sorry, the F is the O, and then put the F somewhere here. What would be the D? what would be the D for that?
Just be from half the house.
So this,
Yeah.
you agree?
Yeah. That's not correct. I no longer agree then.
Then look at here. This is one thing that was the D is the normal distance. The
Okay.
D is the normal distance between the force, between the point and the force. Normal distance. It's very important that we look at it. The D is normal distance. So it's not distance between O and the F, it's the normal distance. So, remember I was talking about the line of action, and says it's very important, we are gonna use it a lot later. What was the important thing about the line of action of the force?
You can move it anywhere up and down the force, you just can't have it swap directions.
So, on the line of action, you basically can slide it up and down, left or right, on the line of action. Do you agree? So, what's the line of action for this one? Then that, so I can just slide that force down, can I? I can slide it down. So if I slide it down, what will be the D?
Should be the exact same, just slid down now.
Yeah. So it's going to be like this. So if I bring that down, so I slide it down, so that would be the D. So this is the D, and the normal again, the normal distance. And again, the moment would be like that. So let's look at another one. So if I have O here and F here. O here, F here. Let's see. Normal distance. So again, they are not in the same location. What will we do? Draw the line of action. So if I draw the line of action, what will be the normal distance? It will be which direction is going to rotate? Yeah, like that. Similarly, if I have it, yeah, I have the O here, and I'm going to have the F, like this. Again, find the normal distance, draw a line of action, then find the normal distance to the line of action. Which direction is going to rotate? So, you got it? What is the D? Yep. Any question about how to find the D? So in 2D direction, in 2D, the D is the normal distance, and to find the normal distance, slide the force left or right, up or down along the line of action. Slide it back and forth until you can draw a normal line from the point to that line of action. In other words, D is the shortest distance between O and the line of action. D is the shortest distance between O and line of action. Any question? Question? So next is the resultant moment. So the how to find the resultant moment. So for the resultant moment, assume I have point O somewhere here. And then I have three forces. So F1 here, F2 here, and F3 somewhere. So if I have these three forces, and I want to find the moment about point O, so I want to find the moment about point O. What I would do that the moment about point O would be the sigma Ft. The moment about point O, this would be sigma Ft. And how I'm going to do that, so it's a resultant moment, I would say. I said, if you want to say resultant moment, what point? So, what are the moments I have? So I have, but this is going to be my D1, this is going to be D2, that's going to be the D3. So, the resultant moment about point O is one F1 D1, and assume counterclockwise is positive. Assume counterclockwise is positive. So F1 clockwise or counterclockwise? It's going to be counterclockwise like that. F2 clockwise. F3 counterclockwise. Counterclockwise. So F1 D1 is positive or negative? So F1 D1 is positive because it's counterclockwise. F1 D1. F1 D2, F2 D2, positive or negative?
Negative.
So F2 D2 will be negative. Minus F2 D2. basically, this is the M1, this is the M2, this is the M3. Principle of moments. So the next is the principle of moments, and we can have it in both 2D or 3D, in the scalar or the Cartesian form. In the scalar format, the principle of the moment would say that if I have a force, assume that I have an xy, then I have a force somewhere here. If I want to find the moment of that force, if I want to find the moment of that force, about point O. So, based on our knowledge right now, how we should do that? If I want to find the moment of F about that point O.
I would say it's easier just because it's 2D.
So right now, if I want to do that, based on what we have so far, that I have to draw a line of action, right? And then find the D, and say, okay, the moment is F times D. Correct? You can do that, but usually it's not a very convenient way of working. Usually that D is not that easy to find. You have to go through lots of calculation to find geometry and trigonometry, some kind of things, so you can find. That's what you can do it right now. The easier way of doing that is that if I have it, so that's a principal moment. Instead of doing it like this, I said, you know what? I will go ahead and I will find that component of that force. So let's say, okay, this is going to be the F on the X, and this is going to be F on the Y. I will find its component. Okay? Now, what's the moment of Fx? If I go ahead and say X, this distance here. If I want the moment of Fx about O. No, it's not that difficult because I can draw a line of action. And I call this D sub Y, D in the Y direction. It's not dy, it's a D in the Y direction, okay? And the same, I will come down here and call this D in the X direction. Now I can go ahead and say, you know what? Moment about 0.0, moment of F about 0.0 was F times D. I know the F, I don't know the D. Instead of doing that, I will go ahead and say, okay, moment about is Fx times dy, d sub y, plus Fy times d sub x. That's going to rotate like this. So basically, instead of going ahead and find the moment of the force, I will find the moment of this component, I will add them together. So that's what the principle of the moment says. That instead of like say F times D, then in this case D is not, as I said, D is not that straightforward to find. Instead of using that, I will resolve it to the Fx and Fy. I find the moment of Fx, I find the moment of Fy, add them together. And then make sure you follow the sign, make sure that you follow the positive, negative sign, whatever you're considering for whatever side you consider to be, whatever direction you consider to be positive. Any question? So these things we're going to use it a lot until the end of the semester. So any part of that you think might need more explanation, just make sure that you ask. But this is something that we're going to use it over and over and over again.
The fx dy, is that still, would that be negative? 'Cause it's,
Yeah, I didn't put a positive negative, but if you write the fx, the fx dy will be negative, the fy dx is positive. So if you want to make that more correct like this. But in general, you can just, when you write it, then you have to make sure which direction you consider positive, and then you put the positive negative there. Let's look at some examples. So, let's start with a simple example and just go ahead from there. So, so the first case, assume there's a wall, there's a beam, and then there's a force, 100 Newton, and then there's a distance of 2 meters. And then it's the point O. Want to find the moment of the force about the point. So this is probably the simplest case that can happen. So how much is the moment?
200.
Clockwise, counterclockwise?
Well, it doesn't matter, we'll put it in this case.
Doesn't matter.
So, negative 200.
So it's negative 200. So if I go ahead and say M is F D is 100 times 2. I assume so I assume counterclockwise is positive. So this is gonna be negative because it's gonna be minus 200 Newton. So next one, assume I have the wall. That, and there is a force here. Is 15 Newton. The distance is 2 meters. Okay. 1.75 meters. Here. So what's the moment about point O? Okay, I want to find the moment about point O. Assuming counterclockwise is what? So that's the force is 50. So know that. What's the normal distance between 50 and the point O? So how is the normal distance?
That's
Is it 0.75 or is it 2? Is it 1.75?
trouble in action.
So correct. So if I draw a line of action, and then normal distance, then the normal distance would be this. So that's a D. Now, is it rotating clockwise or counterclockwise?
Clockwise.
So if I, because I can push it here, if I push it here, it will rotate clockwise. So it's gonna be 50 times 0.75, and it's gonna be positive because it's gonna be clockwise. So the next one goes like that. The pin goes like this, and then goes off. Like this, and then it has 40 palms going down. Then 4. 4. 2, 4. Then 30 degrees. So the point over here and here. What's the moment at what point?
So where is it, or like what is it?
What is it? How much is it? So first of all, the normal length,
Normal length is 4, or no, 2.
Two goes.
Yeah, 2 goes through. Uh,
4 plus 4 plus 2 goes in 3.
so if I draw the line of action, D would be this distance here. Right? That's the D.
Okay.
So I know part of it is 4 foot, I need this rest of that, and the rest of that is 2 cosine 0D.
Which is 1.73.
Okay. So I'm gonna aim about point O and assume counterclockwise positive. Is it clockwise or counterclockwise?
Clockwise.
Clockwise is positive.
That's counterclockwise. It's negative. This one is also negative. There's a it's a clockwise, so it's negative. And it's gonna be 40 times 4 plus 2 cosine 30. Yep. Next one. It goes like this. This. And then we have 60 pounds. By the way, the unit for this one,
Oh, that was fun for the square.
this is one. And this is 45 degrees. Yeah, this is wonderful. So normal distance, what's it? Normal distance,
3, no, that's not right. 3 minus 1 cosine 45.
3 minus 1 cosine 45.
Yeah.
Agree, disagree.
If they're pulling straight out, you're not gonna get any.
It's like pushing the hinge
Yeah,
of the door.
so what are we trying to calculate?
The moment the ball goes forward. Does it cause the rotation or not?
No!
Does not?
If you're pulling just straight back, but you're trying to move it either up or down, there's no chance, because moment is also based off angle, and it's like cosine or whatever, and so if your angle is cosine 180, then you actually end up getting 0 as your force, like it's a multiple of 0. At which point, you've lost all hope.
Where did you got that cosine? 180.
It was something from physics we were talking about, when we were doing
You would have the torque from here to here, so put a torque this way.
there's a torque upwards.
Well, there's a torque that goes here. You push this way, which when you're pushing on this thing, it's not push it up. It's like if you have 2 pounds, you push this.
Yeah.
So
The D is sine 45.
So D sine 45. So again, I draw a line of action to find the normal distance. What's the normal distance? It's gonna be this. D. So look at here. If I put the force here, I can put the force there.
Yeah.
Does it rotate about O or not? Assume there's only O and force, not forget about this shape. If I put the force here and point O, does that force rotate about O or not? Right. If I have O and the force here, and this is D.
Yes, that can rotate around.
So if that rotates, that rotates.
Okay.
Got it? So which way it rotates? Clockwise, counterclockwise? Counterclockwise, so it's going to be positive. So M about point O, assuming the counterclockwise positive. So it's going to be positive. Plus the distance, and so it's going to be, the force is 60, and the distance is 1 sine 45. This is not even 1. This distance is going to be 1 sine 45. Got it?
Yep.
So it's going like this. The O and there's going to be 7. 7 kilonewton and 214. 2, 1, 4 meter. So first question, does it rotate it about O or not?
Yes.
Yeah.
So again, anytime you got confused that force create the rotation or not, remove the object. Only keep the force and the point. Okay? Anytime you got confused if it does rotate or not, remove the object to keep the force and O. If the force rotates about that point O, that object will also rotate. The only way that it does not rotate is that the force goes past through the O. If it goes past through the O, it doesn't rotate. If the force doesn't pass through the O, it will rotate one way or another. Okay. So M about point O, again assuming counterclockwise positive. So is it rotate clockwise or counterclockwise? Counterclockwise, so it's going to be positive. And